Over the last year, we've actually moved on to more and more of the prototyping and scaling. Actually, 3 of the projects, the research projects that we showcased at last year's event, have since been piloted with industry partners.
Which is exactly what I believe Turing is all about. It is creating AI, it's creating technology to serve society in the best way it possibly can.
One of the things that has struck me as we've been working with the Turing is how some of the most productive applications of research come from tangential areas. Another breakout room, we saw the anomaly detection work being used for telecoms. That research actually started in the financial services sector, looking at anti-money laundering platforms, and then jumped across into a very different field.
As director of Turing, I'm obviously delighted that we're able to announce soon the 5-year strategic partnership between ourselves and Accenture.
How can organizations develop AI in a way that identifies and assesses potential imbalances and bias?
Previously, you would have seen banks to use underwriters and big teams of underwriters to make credit decisions. Now we're kind of becoming more and more of a model-driven bank and using models instead to make a large majority of those decisions. We also want to be an industry leader in this area, and hopefully we can showcase some of this stuff to you today, that it can also be taken on board and used in other industries and data science teams to get up to speed. And
the research, in a nutshell, is driven by the fact that AI systems can be complicated. It's important to know that the counterfactuals are not just for banking. They can be used whenever an automated decision is made, be it regression or classification.
Networks, particularly with large-scale clients such as yourselves, are vast and particularly complex. By networks shortly, but in essence, networks underpin so much of the services and systems that we use worldwide every single day. So we've been developing novel algorithms to analyse these large-scale networks, particularly to pick out anomalies and unusual patterns.
That's what the research focuses on, is being able to address this challenge of how we're able to build models that are able to kind of predict the performance of robots in very dynamic spaces, right? Very unstructured environments.
So our research in a nutshell is looking to try and solve complex optimization problems. And the reason we want to do that is because where we have systems with lots of moving parts, if we can run these smart optimization algorithms, we can generate better performance and greater efficiency. I think that this approach, and the literature supports this, that in fact this could be rolled out in many other different problems. Wherever we have expert knowledge, wherever we have a complex system that needs to be optimized, we could potentially apply this approach.